All right, so we're going to go ahead and start on chapter 2. Yes, it is the same chapter and same kind of information that you're going through for your homework starting today on chapter 2, Summary and Learn Smart, but you're getting a different perspective and explanation on the same material, whereas when you do it at home, you get the practice of reading and intaking material on your own, which is really, really important for you on the AP exam. So let me share my screen. And the first thing I want you to do is kind of take a moment to jot down and recall the similarities and differences of eukaryotic and prokaryotic organisms. So pause and write a few down underneath the date for today where you are starting these new section of notes. All right, so the main difference that you should have been able to think about is the lack of membrane-bound organelles in prokaryotic organisms, right? Eukaryotes have nuclei, they have Golgi bodies, they have endoplasmic reticulum, and they have just basically any membrane-bound organelle. And prokaryotes don't show that level of complexity. And that's the main thing that you should have been able to recall when you were talking about those. So the learning objective is a combination of the previous one, which is the bottom half, and then a new one, which is learners will be able to describe differences between prokaryotes and eukaryotes. And that starts from the molecular basis, which is why the chapter 2 notes that we're going to be taking, along with your homework of doing the chapter 2 textbook summary and Learn Smart, is based on basic chemistry. We'll start it today, and then we probably won't finish, but we'll get through at least about half of it. So as a title across your notes in the top, please write chapter 2, basic chemistry, at the very, very top, nice and big. And then the first thing we're gonna kind of discuss is matter, okay? So matter refers to anything that takes up space and has mass. Right, so pause whenever you need to write something down. Okay, and don't get matter confused or mass confused with weight, because weight is specifically when gravity pulls down on you and you exert a force that is weight, right? Mass is just having substance and taking up space, okay? The second thing we're gonna define is elements. So a substance that cannot be broken down to simpler substances with different properties is an element, right? Elements have special properties. For example, metallic elements tend to be solid at room temperature and then liquid once they're heated up pretty hot, right? At room temperature, some of them are bendable, right? If you think about gold rings, the more gold there is, the softer it is, so it's actually bendy, okay? There are other substances like chlorine that are gases at room temperature, and those are just some of the properties of elements, right? If you mix them together, you can create compounds, but if you break them down into their simple components, they are individual elements. And those are the same things that you find on the periodic table, like the one that I attached to this day's class. So common elements found in living organisms are CH&OPS, and these include carbon, C, hydrogen, H, nitrogen, N, oxygen, O, phosphorus, P, and sulfur, S, okay? So carbon is mainly known for its carbohydrate structure, right? So like carbon rings make up plant walls. Carbon rings also make up a lot of the sugars that we consume and taste as we eat, and that we intake for energy and build our own bodies using carbon. Hydrogen is in almost most, it's basically in every single compound that you can think of in organics. It's also in water. It's part of the water molecule. Now, nitrogen is kind of weird because it's all over the air, but we don't actively use it in the air, right? But we use it when we build proteins. We use it in our DNA. So it's actually really, really important. Oxygen is important, you know, because we breathe it to survive, but it's also important for oxidizing processes for our metabolism, for breaking down a lot of things. Phosphorus, you might not know what that is, but it's a huge component of your DNA, and it's also in a lot of proteins. And then sulfur bonds are super important in proteins as well. And I say proteins a lot because a lot of the physical structures that we see and are made out of involve these. So that's why they're important to organic life. So the atom is the smallest part of an element that displays the properties of the element, okay? So protons are positively charged. Neutrons have no charge and have zero charge, so they're neutral, neutron, neutral, think of that. And electrons have a negative charge. So protons or neutrons are kind of big, and they're both found in the center right here. So the blue and the red right here represent the neutrons. They're found in the center of the atom. And they're pretty much, when you add them together, you get the mass of the atom, or you get the mass of the atom of that element. And different elements have different numbers of protons, neutrons, and electrons. And that's how they have different properties from each other. Electrons, on the other hand, are really, really small and basically have no mass. And so they are represented by these dots along the outskirts of the atom. And honestly, they're not staying still like the protons and neutrons are in the center. The electrons on the outside are whizzing around, moving really, really fast in kind of these figure eights or these circular loops around their central positive and neutral components over here. So together, this is the three main components of an atom. Now here we have atomic number, which is important because atomic number represents the number of protons an element has, which accounts for the unique properties of this type of atom. So every single element has an atomic number, and the atomic number is the exact same number as the number of protons, aka the number of positive charges in the center of the atom. Okay, so we recognize all of these elements based on their proton counts, and their proton counts are what make them unique from one another and make them have different properties and behave differently and interact differently. So here we have atomic mass. So atomic mass is the average of the atomic mass units for all isotopes of the atom. And isotopes are just different forms of the same chemical element, okay? Because some of them are radioactive, some of them have extra neutrons, right? But they're all containing the same number of protons. So they're considered the same element. They're just isotopes because they're different versions of the same element, okay? Electrons are so small that their AMU is considered zero. That's what I mentioned earlier when I said they were really, really small. That's why I do them as dots up here instead of larger massed molecule pieces here. Okay, so again, mass number is the sum of protons and neutrons in the nucleus because electrons are so small that they basically have no mass. So here, carbon has an atomic number of 6 because it has 6 protons. Now, it weighs around 12 AMU, or atomic mass units, because 6 protons plus 6 neutrons is about 12. The discrepancies here are because this is the weight of carbon of all types, of all isotopes. So some carbons have extra neutrons, some carbons have less neutrons based on what's going on with them in their chemical structure. But when you average them all out, there are a lot more, even though it's still rare compared to the normal 12 AMU carbons, there are more that are heavier than 12 than there are that are less. So the few that are heavier cause the average of all carbon atoms to be a little higher than 12. Now we have isotopes. I kind of want to go back and explain since earlier we mentioned them. So isotopes are atoms of the same element that differ in the number of neutrons, right? The protons stay the same because if the proton changes, the atomic number changes. And if the atomic number changes, then the element's identity has been compromised and it is now different. Okay, so an example is carbon-14. Carbon-12 is the regular carbon. It has 6 protons and 6 neutrons. Carbon-13 means that it still has 6 protons, but now it has 7 neutrons. And then carbon-14 is the next most common after carbon-12, and it's 6 protons and 8 neutrons. So again, the proton number always stays the same, but the neutrons change. So carbon-14 is useful to humans because we use carbon dating. Carbon is intaken through ingesting foods when an organism is alive, and once the organism has passed away, it can no longer intake carbons, it can no longer intake new carbons. And there's a certain ratio of carbons that are actually not carbon-12s, and they are carbon-14s. But carbon-14 slowly break down into nitrogen. So based on the time, or based on the percent that a fossil contains carbon-14, you can tell how long it's been dead for, or when it last lived, because you can tell when it stopped taking in the carbon-14, because there's only so much little left in it, and it's all been broken down into nitrogen. Okay, so carbon dating is useful for kind of identifying the age of fossils, and it's only because we discovered that carbon-14 is a thing. Okay, Valence electrons, we talked about electrons, right? Those little negatively charged things on the outside of the nucleus. Valence electrons are the outermost shell of an electron, of electrons on an atom, which helps determine the atom's chemical properties, right? So the most outside part of the atom is the part that interacts with the surroundings around it. And so the valence electron shell, the one that contains the outermost electrons, interacts with the environment and interacts with other elements. So that's why we want to talk about them a little. The valence shell determines if the atom gives up, accepts, or shares electrons. So here we see an atom that has a full valence shell, meaning that there are 1, 2, 3, 4, 5, 6, 7, 8 on the outermost ring of the electron shell. So having a full set means that it is steady and stable. It doesn't need any more, and it doesn't need to get rid of any because it has 8. Okay, 8 is always a stable number unless it's the first ring, the closest one to the nucleus. That one only wants 2. Okay, so that's called the octet rule because atoms like having 8 electrons on their valence shells. Now, if, for example, this shell only had 7 and it wants 8, do you think it's more likely to give up all 7 one at a time, or is it easier for it to just steal 1 from another element? Right, it's going to be easier for it to steal 1 instead of trying to break all the 7 away to reveal the 8 underneath for a level of stability. So the closer you are to 8, the more likely you are to take electrons and have a higher electron negativity, right? You have a high affinity for electrons because you want them so bad to fill up that 8. Now, if you only have 1 or 2 on the outside shell, you probably rather just give them away and then just have a positive charge, because if you give them away, then you'll have the octet from underneath revealed because your ones on the outside that were just kind of unstable are now gone. So the octet underneath that is stable is revealed and you're chilling, right? So if you have less, you're less electronegative because you're trying to give them away. And if you have more in your valence shell, then you have a higher electronegativity and you want the electrons a lot worse. Okay, so again, that's the octet and 2A8 rule. So if an atom has more than 1 shell, then the outermost shell is most stable when it has 8, and it will do almost anything to make sure it has 8. If the atom only has 1 shell, then it's stable with 2. That's this innermost shell. It only holds 2, partially because of spacing. Okay, here we have the definition of a molecule. Again, make sure you pause whenever you need to. You can pause at each section or at the end of each page. A molecule exists when 2 or more elements bond together and is the smallest part of a compound that retains its chemical properties. Pretty self-explanatory. So when you have elements, they bond together, you get a molecule. Okay, compounds are usually a broader category, right? Because they are multiple different kinds of chemicals bonding together. Molecules can also exist where it's just nitrogen bonding to nitrogen, or carbon bonding to carbon, or hydrogen bonding to hydrogen. Now we're going to talk about 4 types of different bonds. Okay, so ionic bonds are the first ones that we're going to talk about. And they're kind of interesting because we see them on an everyday basis. If you ever ate anything that had salt in it, you've consumed ionic bonds, right? So ionic bonds are when an electron is transferred from the less electronegative atom, right? The one that wants to give it away, doesn't really care for it because it would rather have the stable octet underneath, to the more electronegative atom, the one that really, really wants the electron because they only need 1 or 2 more to complete their octet because they have so many already. Thus, one atom becomes negatively charged, right? If you originally are balanced with 3 positives in your nucleus and 3 electrons on the outside, and you give 1 away, you're going to have 3 positives and 2 negatives. Therefore, you're going to have a positive charge overall, right? And then if you have, say, if you have 7 electrons in your outer shell, and then you have 7 protons, right? If you have 7 and 7, but you gain an electron, so you gain an extra negative, then it's -8 and +7. So there's a negative charge if you're gaining the electron, okay? So one atom will become negatively charged and the other becomes positively charged. And now because they're oppositely charged, they are attracted to each other, and that is the ionic bond. Okay, so again, just to re-emphasize, electronegativity, this is a large definition. You can also just explain it as if it's closer to an octet, it has high electronegativity because it wants to take an electron. And if it's really far from an octet and would rather have the octet underneath, then it would just give away an electron and it has low electronegativity, right? The term electronegativity just refers to how strongly an element is holding on to its electrons, right? If you have a high one, you're a strong hold. And if you have a low level of electronegativity, you have a low hold and it's loosely allowing the electron to leave more easily. Okay, so the electronegativity in ionic bonds is really, really different between the two atoms that are interacting, right? One literally just is like, get it away, you can take it. It has almost no electronegativity. And the other one is like, oh yeah, I really want that, so it's gonna take it without any second thoughts. Okay, so in this drawing, you can see this is NaCl, which is table salt, the normal salt that you eat in your foods. So originally Na is sodium and Cl is chlorine. And together they make sodium chloride. But in order to do so, right, if, as you can see in the valence shell of sodium here, there's only one, and that is very, very unstable because underneath it has an octet that it would much rather have showing. Okay, so sodium has a low electronegativity because this one is just being loosely held on. It's far away from the nucleus and it's super unstable. So it's very, very likely that it will just give it up. And it's going to give it up to chlorine. Chlorine, which if you see on the outside, has 7 electrons, which means it's super, super close from completing that stable octet. And it just needs that one last electron. So it's really, really electron hungry and has a high electronegativity. So it's going to happily accept that electron from sodium. And together, they are now going to have, sodium is going to go down to that stable octet. Chlorine is going to fulfill its new stable octet. And if you see here, sodium has 11 protons in the center, but now it has 1 less, and it has 10 electrons on the outside. So it's positively charged. And then over here, you can see that the chlorine gains an electron, so it has 18, whereas it still only has 17 protons, so it has a negative charge. And now they stay attracted to each other because one's positive and one is negative. The second type of bond is actually technically broken down into 2 kinds of bonds. And in general, covalent bonds are resulting when 2 atoms share electrons in such a way that each atom has an octet of electrons in the outer shell, with the exception of hydrogen because it only has 2. It's a tiny atom. Okay. So the difference between covalent and ionic bonds are because covalence is sharing electrons, right? Sometimes you have it, sometimes you don't. Sometimes the other has it, sometimes you have it, okay? In ionic, once you give away that electron, it's no longer yours. It's a give and take, and that's it. Okay, so covalent is sharing, right, between 2, and then ionic is just giving it away, and then that's it. Okay, so there are 2 kinds of covalent bonds. The first being non-polar covalent. And so non-polar covalent means that the electron is shared equally. So the electronegativity between the 2 elements or the 2 atoms that are going to be sharing this electron have an even pull. For example, if you and your twin are fighting over the same piece of candy, you guys are pretty much the same strength, same height, same way of fighting because you're raised similarly, right? So you're going to be able to pull for that candy an even amount. Actually, candy is probably not a good example. Maybe get toy because it just doesn't go away. So a toy, you're going to play with a toy an even amount, and then you're going to fight for it, and then the other person's going to play with it for a little bit, and then your parents are going to make sure that the other person gets it back, and then trade it off again. And you guys will pretty much get an even amount of time sharing that toy, which is like the electron, okay? Again, the only reason they're sharing the electron is because when they share it, some of the time they have an octet, and being fulfilled and stable for some of the time is better than none of the time. So they would rather share than not be stable. Okay, so usually nonpolar ones can occur between when you have 2 of the same elements sharing the electrons. For example, oxygen and oxygen, right? They're going to have the same pull on the electrons because they're the exact same element. Over here, the other kind of covalent bond is a polar covalent bond. And we say poles, like North Pole, South Pole, because there's a positive and a negative charge to those poles, right? It's the same idea. So electrons are shared unequally because it's two different elements that are sharing the electrons. So here we have H2O, which is water. So there's one big O, which is oxygen, and there's two hydrogens, and the hydrogens each have one electron, and the oxygens each have two spots for electron sharing. Now, the oxygens, first of all, have a lot more protons, so they have a lot more positive charges to pull and attract the electrons, whereas the hydrogens only have one, so they're kind of weak on the pulling ability, right? And they only have one little shell, so they're not big either. They're not really going to be able to, fight for their electrons very hard. So when this happens, the electron actually sits on the oxygen instead of on the hydrogen a lot more. So if you were going to randomly grab the electron at any time, you would probably grab it off the oxygen more often than you would grab it off the hydrogen, because it just spends more time on the oxygen because it's strongly pulled towards the oxygen. And that makes it uneven, right? So if the oxygen gets extra negative charges on it most of the time, then it's going to be kind of negative on that side. And if the hydrogens are not having their positive cores or their nuclei balanced out by the electrons a lot of the time, because they're always all the way over at the oxygens, then the hydrogen side is going to be kind of positive. And that's why the plus is on this side. So we use this weird shaped arrow to represent which side is the positive side, which is the hydrogen side. And then it points towards the negative side always. And that's just how we draw dipoles. Okay. You would never draw a dipole on a non-polar bond because there is no positive or negative side. They're always equally shared. But because these are unequally shared, one side is going to be more positive than the other. And as the electron spends time unequally, the dipole is present. Okay. The last type of bond that we're going to talk about is the hydrogen bond. So when the differentially charged poles of a polar covalent bond cause molecules to be attracted to other molecules, a single hydrogen, it forms a hydrogen bond. Okay, so a single hydrogen bond is actually not very strong. But when you have a lot of them together, it creates a very, very strong pull, and they create like things in water like surface tension, like when it's hard to break out of the water, right? Or when you, for example, if you drip water onto a penny and you notice that it can stay and create a huge bubble, that's because of hydrogen bonds. Okay, so it's kind of amazing feats of nature. Again, so hydrogen bonds are only possible because when hydrogen bonds with something, it always forms a dipole if it's not with itself. And when it forms a polar covalent bond, then you can have different molecules actually attracting to each other, because in this picture here, you can see, remember the hydrogen has a kind of positive charge based on this dipole, and the oxygen has a negative charge based on this dipole, right? Because the arrow is pointing to it. So the negative part of the oxygen is gonna kind of attract to the positive part of a hydrogen of a separate molecule, because it's like magnets, positives and negatives attract to each other. And then maybe this positive is attracting to this oxygen's negative on a different molecule, or this positive over here on this hydrogen is attracting to another molecule's negative oxygen over here. And molecules, for example, like water, connect to each other and actually end up jumbled together quite strongly because of these hydrogen bonds. Okay, so to summarize, after you've paused and written your notes and reviewed all of those things, I'm going to ask that you write a really, really short essay kind of describing them, just to show me and yourself that you understand how these bonds work and maybe why they're important. Okay, so here's tips for writing a free response essay. I've also posted it in the following assignment. And your short essay question to close out this class is to explain the properties of each bond and how they affect the interactions with other molecules. So we talked about polar covalent, non-polar covalent. Remember, polar is when it's unequal sharing. Non-polar is when it's equal sharing. Ionic, when it's not sharing at all, it's just an exchange almost. And then hydrogen bonds, which is based on polar covalent bonds, but specifically relating to molecules that hold hydrogens in them, and maybe how they affect other molecules. Okay, so if you need to re-watch the video, or if you want to look up any of these terms for explanations, that's totally fine, as long as you are explaining them in your own words in a summary on Google Classroom. Your homework that extends to next Tuesday, again, is to finish your Chapter 2 textbook summary and Learn Smart. Make sure that you submit them online. And that's all we have for now for Chapter 2. I will be posting a demo on that kind of introduces the water properties we'll be going over next. So feel free to view that after this.